Good morning, everyone. Today we will start our next unit, which is unit number 3, the control of induction motor through the stator voltage and stator frequency. So unit 3, 4 and 5, these 3 units we will control the AC motors. Out of 3, 4, 5, only 3 and 4 deals with induction motor. 5th unit deals with synchronous motor. Coming to unit 3 is stator control and unit 4 is a rotor control of induction motors. Okay, so now let's see the contents of unit 3. So these are the contents given in our syllabus. The first one is variable voltage characteristics. So we have to control the induction motor by keeping all other parameters constant, and the variable parameter is only voltage. So we need to control the we need to vary the voltage in order to control the induction motor, speed of the induction motor. So we will draw the speed torque characteristics here along with the waveforms, and this voltage control can be done by AC voltage controllers. We know what is AC voltage controller. AC voltage controller controls and converts input AC voltage to output AC with variable voltage. So we can regulate the voltage magnitude using the AC voltage controllers. Okay, so in the variable voltage characteristics, we need to control the voltage, right? Stator voltage. Stator voltage, remember this word because unit 3 deals with the stator. So we need to control the stator voltage, so that can be carried out with the help of AC voltage controllers. So we will see the circuit diagram of control of induction motor with the help of AC voltage controllers and the respective waveforms along with the speed torque characteristics. And in the speed torque characteristics, we also find the voltage term, because with respect to the stator voltage, how the torque and speed relation will be changed, that we need to see in the speed torque characteristics. In the similar way, variable frequency characteristics. This is AC supply. So we have two parameters to control. One is the magnitude and the second one is the frequency. So magnitude can be controlled with the help of variable voltage characteristics or the variable voltage. Frequency can be controlled by using different methods. We know the inverter concept. We have seen the inverters, different types of inverters in the power electronics subject. So using the inverter, we can control the frequency. And similarly, using the cycloconverter also, we can control the frequency. So here you can see clearly the variable frequency control of the induction motor can be carried out with the help of voltage source inverter and current source inverter. So VSI and CSI, voltage source inverter, current source inverter, along with the cycloconverters. We know voltage source inverter, what is voltage source inverter, and we know what is current source inverter. We have seen it in the power electronics subject. So with the help of voltage source inverter and current source inverter, we can vary the frequency and we can control the induction motor. How it can be done, that we will see in this section. And similarly, the cycloconverters. We know how the cycloconverters will operate. We know how the frequency it can be controlled with the help of cycloconverters that we have seen already, and we have done in the laboratory also, how the control has been taken out with the help of cycloconverter. So using a cycloconverter, how the frequency will be controlled, that also we will see in this chapter. And the PWM control. We know PWM, what is PWM? PWM is pulse width modulation. So with the help of pulse width modulation, we can control the speed of the induction motor. How the PWM control can be carried out, that also we will see in this concept. And these are the major topics. Only two major topics. One is variable voltage characteristics, and the second one is variable frequency characteristics. In the variable voltage characteristics, AC voltage using AC voltage controllers, their waveforms and speed characteristics are the subtopics. Similarly, in the variable frequency characteristics, the frequency variation can be carried out with the help of VSI, CSI, and cycloconverters, PWM control. All are the subtopics in the variable frequency characteristics. And after completing these topics, we will see the comparison between VSI and CSI, means voltage source inverter and current source inverter. Already this comparison we have seen in our power electronics subject. Once again, we will see here. And we will also see the speed characteristics for variable frequency characteristics also, and the problems on induction motor drives, and the closed loop operation of induction motor drive, and that is block diagram only. So these are the topics that we need to cover in this unit. So this unit completely deals with the stator voltage and stator frequency control. Simply stator control of induction motor. If you want to learn stator control of induction motor, then this unit will help us. In the unit number 4, we will use rotor control concept. To control the induction motor, we will use a rotor control concept in the unit number 4. Okay, that we will see later. Now, before going to the unit or the subject, we need to know the induction motor importance in the speed controlling mechanism, because this subject deals with the motor control. So we need to see how the motor control is done, and before that we need to see the importance, why we need to control the induction motor, why we need to use the induction motor in speed drives. Speed drives means we have two different kind of speed applications. We have two different kind of speed applications. One is variable speed applications, and the second one is constant speed applications. So for variable speed applications, which motor is effective, and for constant speed applications, which motor is effective, we need to identify that based on the performance of these drives. Okay, so that we will see what is the importance of induction motor, and how the induction motors are classified. Of course, we have seen them in our machines 2 subject, which is AC machines subject. Again, we just briefly we will recall the basic concept with respect to the drive concept, with respect to the speed control application concept. Okay, so induction motors are used in the past in many applications where a constant speed is required. So in the conventional methods or in the olden days, induction motors are used for constant speed applications only, because without the induction motor, some conventional methods are there in order to control the speed regulation constantly, but they are very expensive and the efficiency of those conventional systems are very, very poor. So in order to avoid that, induction motors are adopted to regulate or to control the constant or to maintain the constant speed of the drive. Okay, but variable speed applications have been dominated by DC drives. In the olden days, variable speed applications, we use DC drives in the olden days. Availability of the thyristors, power transistors, and other IGBT, MOSFET, GTO switches have improved the development of induction motors towards the variable speeds, because induction motors previously used to control the constant speed, but because of the development that happened in the power electronics, now the induction motors are used in 1 second. Okay, so in the olden days, the induction motors are used only for the constant speed control only. But the development that happened in the power electronics, that leads the induction motors used in the variable speed applications also. The main drawback of DC motors is the presence of commutator, because we use a commutator on the DC motors in order to convert that AC generated EMF into a DC value. So because of that commutator and brushes to collect the current that is generated by the motor, so these are the major disadvantages. These commutator and brushes will increase the weight and the size of the motor, which means the cost of the DC motor will also be more. And not only these brushes and commutators definitely requires a frequent maintenance, and these cannot be adopted for explosive type of applications like petrol wells or diesel wells or any other flammable things. In those applications, we cannot adopt the DC drives. Because of the brushes, we will get sparks. So those are not suitable in those type of applications. But the induction motors are very rugged, very lighter, and very cheap. And the size of the induction motor is also very, very small and very efficient. And here the maintenance is also low compared with the DC drives. So all these are the different advantages that are surrounded with the induction motors when we compare with the DC motors. So size is less, the size of the weight is also small, and the cost is very cheap. And all these are the different advantages uh, with the induction motors. So these advantages, along with the development that had happened in the power electronics subject, made us to look into the induction motors for the variable speed operations also. So for the variable speed control, induction drives are most used drives nowadays, and they have a various number of applications, like they will be used in fans, blowers, and mills, cranes, conveyors, etc. So these are the different applications that induction motors are using, and these are the dominant speed control drives that are using present days because of the advantages that they have when compared with the other DC motors, right? And now coming to the induction motors, three-phase induction motors generally classified into two types. You know them. One is a squirrel cage induction motor, and the second one is wound rotor induction motor. The wound rotor induction motor is also called as a slip ring induction motor. And based on their construction, the names have been given as a squirrel gauge as well as the slip rings, wound rotor or slip rings. In a squirrel gauge and wound rotor induction motor, the both categories, the stator carries three-phase balanced distributed winding. So the stator is same for the both, means a squirrel gauge motor as well as the wound rotor motor. For these two, the stator construction is very much same. The winding is three-phase winding, which is very balanced distributed winding for these two. Coming to the rotor, the construction is different. We have the constructional difference between squirrel gauge and the wound rotor or the slip ring. The rotor of squirrel gauge motor contains longitudinal conductor bars which are made with of copper or aluminum bars, and those bars are short circuited at the both sides. So on the rotor we will place copper bars or aluminum bars. Those bars are short circuited at the both ends. At the both ends, both are short circuited. While in the wound rotor or the slip ring motor, that slip ring motor in the rotor part is also contains a three-phase distributed winding which is having the same number of poles as the stator. So simply we can say the stator and rotor of a slip ring induction motor looks like the same. So this is the difference between the rotor connection for squirrel gauge motor as well as the slip ring induction motor. Although you know all these things, but I wanted to recall once again the types of induction motors. And now you understood the concept of or the importance of induction motor in constant speed drives as well as how they evolved into variable speed drives with the help of power electronics. So in order to reduce the size, in order to reduce the cost, in order to make it small, or in order to make it more efficient, the entire system of DC motors can be replaced with the induction motors in the variable speed applications also. Now, let's see the variable voltage characteristics. So, in order to draw the variable voltage characteristics, which means we have to draw here the speed and torque relation, we have to derive the torque expression in terms of speed along with stator voltage, because here the variable value is the voltage that is applied across the stator terminals. Okay, so keep remember that we need stator control. So in that stator control, we are controlling the stator voltage. So this concept is variable voltage. Okay, so now you can see here this figure shows the per phase stator referred equivalent circuit diagram. Figure A is a per phase stator referred equivalent circuit diagram. You can see the rotor terminals or the rotor elements are referred towards the stator. That is the reason why here dashes has been placed, and this is small s, capital R dash by small s. This small s represents the slip. This stator referred equivalent circuit diagram, how this circuit diagram have been derived, that all those things we have seen in the machine. Let me tell you the elements that are used here. Phase neutral, this is per phase circuit. So a single phase representation is shown here because this is a per phase circuit. And next, V is the stator voltage. This is the stator voltage. And IS is the stator current. Sorry, this is XS or not RS because this is winding. This is XS, which means stator winding reactance. And here it is RS, which means this is stator winding resistance, because each winding will have a inductance value and a resistance value. Those are represented as RS and XS. RS means stator, XS means also belongs to stator. And coming to the rotor, XR dash and RR dash by S, where S is the slip here, XR dash is the rotor, stator referred rotor reactance. Similarly, RR dash is the stator referred rotor resistance, because this is a stator referred equivalent circuit. So the rotor parameters are called as stator referred rotor parameters. You know them very well. We have seen them in machines too also. And you can see the current here, which is RR dash. This is also the stator referred rotor current, that is in amperes. And in between stator and rotor terminals, we can see the leakage inductance or the magnetizing inductance. You can say simply the leakage inductance. And this leakage inductance can be shown as XM, which is leakage or magnetizing reactance. And IM is the current that is taken by this leakage inductance. And this figure B shows the transferred circuit, simplified circuit. Since this stator impedance drop is negligible when compared with the applied voltage, this drop is very, very small. The stator voltage drop is very, very small. So for the convenience, I am transferring these two stator elements from here to rotor side, because the voltage drop is very, very low when compared with the input voltage. So I am transferring this stator element towards a rotor side. So after that, we will get this figure B. You can see just these two elements are transferred here like this, and rotor elements are same, and this magnetizing inductance, everything is same. So this is for our convenience. In order to derive the torque expression, this circuit will be used. This figure B will be used. And here the terms have been given clearly. You can go through them, each and every term. And now let's see the derivation of the torque in terms of speed and input voltage or stator voltage, because we need to plot the speed torque characteristics. So for plotting the speed torque characteristics, we need to derive the torque expression of the induction motor. So the torque expression of the induction motor, the torque developed in the induction motor, this expression or this equation is very much important. So first we know the slip S. We know the definition for slip, which is the ratio between the difference of synchronous speed to the actual speed, synchronous speed and the actual speed to the synchronous speed. So this is the slip equation, where omega ms is the synchronous speed, omega m is the actual speed of the machine. We know how to calculate the synchronous speed, which is 120 f by p, but here it is omega, not n. So this omega can be calculated with the help of n, because omega is equal to 2 pi by 60 into n. We know this relation. So n is 120 into f by p, where f is the frequency, supply frequency, p is the number of poles. So omega s can be written as 4 pi f by p, that is in radians per second. Omega represents radians per second. N represents revolutions per minute, RPM. Okay. So slip equation is identified as equation 5.1. So from this equation, we can write the actual motor speed, which is omega m is equal to omega ms into 1 minus s. This can be derived from equation 1. See, you can cross multiply this omega ms here and write omega m equation. Omega m is equal to this, omega ms also will go this side, and you will get omega m is equal to omega ms into 1 minus s. This will be our equation 5.3. And from figure 5.1b, we can write the stator referred rotor current. Let's see what is 5.b. See, this is our figure 5.b. Right. Now you can see the IR dash here, which is on the rotor circuit. Now this current can be calculated. Current can be calculated by this formula V by R or V by Z, we can say. V by Z, I'll write Z here because we are having resistance and reactance both. So I will write here V by Z. So using this formula, we can write IR dash. So see, V is the input voltage because that is parallel. See, here the voltage is same because both are parallel. So here the voltage is V, and the Z can be calculated here. You can see two resistors are there which are connected in series, and two inductors are there which are connected in series. So series connection means we simply add those two resistors and simply add those two reactance values. Then you can see V by Z formula. So V by, so we have added both the resistances here and we have added both the reactances here, because this reactive term is a imaginary term. So that is the reason why the J is represented for the reactive terms. So this is the IR, which means the stator referred rotor current. Okay, so this is represented as equation 5.4, and the magnitude of this value can be calculated as this, because this is a Z. So in order to get the Z magnitude, square root of resistance square plus reactance square is given to calculate the magnitude value. We have these are the basics that we can see, we can learn from electrical circuits. And this equation as represented as 5.5. So we need to calculate the torque. So torque can be calculated. We know the power value, power equal to speed into torque. Speed into torque. We need to calculate the torque. From this expression, we need to calculate the torque. That means we need to obtain an expression for the power. So for that, we have considered the power that is transferred from the stator to the rotor. So the power transferred from the input to the output, that power is also called as air gap power. Simply PG is equal to 3 into IR dash square into RR dash by S. Because these parameters are stator referred parameters, we know power is I square R formula. So with the same formula, this is three-phase circuit. So the power transferred from the stator to rotor can be write as PG is equal to 3 into IR dash square into RR dash by S. And this is named as equation 5.6. And we know we have a few losses that will occur in the induction machine, and majorly of rotor copper losses. So the rotor copper losses are given as 3 into IR dash square into RR dash. So all these equations we have already seen in our machines. And this equation, this copper loss equation is represented as 5.7. So the total net power that is produced across the output terminals of the motor, or simply we can say the power developed in the rotor, is the stator power which is transferred to the rotor minus the losses. So PG minus, which means equation 5.6, minus the copper losses, which is 5.7. So substitute here, then we will get the developed power across the rotor terminals. So the developed power, which is PM, is equal to, you can see here, you can simplify this. 3 into IR dash square is constant here and here. So uh, uh, bring it common and you simplify this, you will get 3 into IR dash square into RR dash into 1 minus S by S.